So I want to call for the next talk,
Yes.
which is Ultraviolet Spectroscopy of Planets by Paul Feldman.
Okay, well, I'm very pleased to be able to give this talk. I met Charles first in late 1970. I come to Hopkins in 1968 and got drafted by Ebert-Fastie to work on the Apollo 17 spectrometer. And Charlie Barth and Gary Thomas were co-Is here at Colorado. And it was my first ever visit to Colorado. Bill had us come in, stay at the Harvest House. It's now the Millennium, which has gone downhill. But anyway, we got in at night. He put me in a room where I would wake up in the morning and see the Flatirons. And I was the kid who grew up in New York City, and it was quite an impressive sight. They also took me to a restaurant called the Catacombs, which I had not revisited, and I actually went there last night. It's no longer a restaurant; it's a bar in the Boulderado, but they have a tapas menu, and I enjoy going back, for old time's sake. Anyway, this is a huge topic, so I better get going. And what I'm going to do is, I obviously can't talk about the topic I was assigned, but I will focus on some stuff from the 1960s and how some of these UV spectroscopy instruments got put onto planetary missions. And there's a long legacy. I mean, this is really, I think, a great insight from Barth. He had been a student of Joe Kaplan at UCLA, and he knew molecular spectroscopy in and out. And here's my topic: ultraviolet spectroscopy of planets. Now, this is a dog-eared copy of a JPL report published in 1965. I must have stolen it when I left NRL because it has an NRL acquisition number on it. But it's got in it, a few pages with the basic equations of how you derive densities from measurements of brightness. And he's got lots and lots of tables of very interesting, all the molecules that you can imagine, including nitric oxide, but also water, CO2, CO. And basically, it's a handbook. And the reason it's dog-eared is because I've used it for 30 or 40 years as a quick reference to what molecule is this, or what can I expect from a given molecule. Very, very handy. Okay. This is now a condensed version of that report from Applied Optics, published in 1969. And again, it says planetary ultraviolet spectroscopy instead of ultraviolet spectroscopy of planets. And there's a subtle difference there, and Amanda will talk about some of the other aspects of planetary ultraviolet spectroscopy later today. But basically, there are some very interesting points here. He says the observation of these spectra from planetary spacecraft is accomplished by observing the bright limb, disk, terminator, and dark limb of the planet with a telescope and scanning UV spectrometer. Then he goes on. He determines whether molecules basic for life are present in a planetary atmosphere, and he's very prescient in this abstract. And the idea for the scanning spectrometer came from Ebert-Fastie, who at the time that Charlie was at JPL. Remember, we heard that after his PhD, he did a postdoc at JPL before coming to LASP. And Ebert-Fastie, who was my mentor at Hopkins, was actually a student. He wasn't really. He worked with Hermann Pfund of the Pfund series back during the war, and Bill had the distinction of having a professorial appointment at Hopkins without ever having completed either his PhD or his bachelor's degree. And Bill reinvented, or he found that this fellow Ebert, back in 1899, had invented a spectrograph design, which was very, very simple. It lent itself, again, these papers were published in 1952, and Bill was a consultant to JPL in the summers. Again, I must apologize, I'm not a science historian, I'm one of you. And again, I wasn't a participant in what happened in the 60s, but there are a lot of what you say, just discussions and common. I can't say here. It's not hearsay, but basically, I didn't do a very thorough investigation of what I'm telling you. But anyway, Bill would go out to, from what I remember, he would, from lunchtime conversations, he would pile his family into a car and drive across the country and spend a few months at JPL. And that's where he met Charlie. And they latched on to this spectrometer. Here you see a quarter-meter Ebert spectrometer. It was very simple. It was just a piece of glass with a concave sphere in it, very easy to make a concave sphere, and a small plane grating, and a scanning mechanism. And then you put photomultipliers. One of the secrets was this baffle, which is a multi-segmented baffle, which kept out stray light from, when you're looking at a planetary atmosphere, you don't want the light from the disk. And here you see, this picture was shown in Scott's talk. I don't know where he got a color version of it. I've never seen the color version of this. This is John Deering, who was then a young assistant professor of chemistry at Hopkins. Fastie, who always wore a bow tie. That's from being, so when you worked with machinery, you wouldn't get your tie. That's when people wore ties. You wouldn't get your tie caught in the lathe. And Charlie here, the photographer has Charlie twisting a pump out port. It's not really not a dial or anything. It's a good pose for the photographer. I hate to say this, but this is the third person in this photograph whose memorial I've spoken at. So it's it's historical. This is December 1964. This was at Wallops, and the rocket program was run by Goddard, Greenbelt, and the instruments were so cheap to build that they just threw them into the water. I mean, they launched them without a parachute. These were atmospheric measurements. Here's another one from that same session. Again, Charlie on the right. This time he's holding, looks like a dental mirror, and two other gentlemen from Goddard. And then one more picture from White Sands. This was when they were doing an experiment to look at Comet Ikeda Secchi, which was a sun-grazing comet in the fall of 1965. It was very difficult to do because it was too close to the sun, and we learned from that experience when we designed our experiments for Comet Kohoutek in West in 1974. That was what I was involved in. Now the Ebert, it's not really a spectrometer, it's a monochromator, because it basically passes one wavelength of light at a time. So you have a single pixel detector, which in some ways makes life very easy, because you don't have to worry about flat fields and all sorts of other calibration problems. So this is a miniaturized version. It looks very small, but this is a big hand. Fastie was 6'4". Anyway, beginning in 1972, this 8th meter was flown on numerous sounding rockets, including the first of what became the Solstice series of Solar Stellar. I think you were involved in that, Gary, weren't you? And it's used for many, had many applications on various sounding rockets. Okay, so Charlie was at JPL at the time when they were planning the Mariner missions, the first series of Mariner missions to Venus and Mars. And the first one to Venus, for some reason, all the published literature has 5 in Roman, where I just did it in Arabic. But anyway, all the other mariners had Arabic numerals. But anyway, let me get to where I can see what I've written here. I can see it on the screen, but I can't point at it. Is that this is now the Lyman alpha airglow of atomic hydrogen is measured in the outer atmosphere of Venus, show that atomic hydrogen is present. That was a great discovery. It measures the temperature of the upper atmosphere, and it says an ultraviolet airglow of oxygen is not found. And an ultraviolet night glow was observed on the dark lens. Well, it took a while to sort out what was going on. And one of the things that I'm not going to talk about, and which Charlie wasn't really involved in too much, was the use of telescopic instrumentation from above the Earth's atmosphere for the spectroscopy of planets. So here we have a sounding rocket. This is Gary Rotman's PhD thesis. He didn't even remember that was what his thesis was. Basically, here is the oxygen line. It's just an increase in sensitivity. This was a small prism scanning monochromator that Warren Moose and Fastie developed at Hopkins and flew on a rocket. This is at the beginning of the pointed sounding rockets. A lot of what Phil showed you are rockets that don't really need to be pointed accurately at a stellar or some astrophysical source. And in the early 70s, they were developing the pointed sounding rockets, and they were able to point Venus and Jupiter, were both very bright and easy to point at with the existing techniques. But there's this bump here. You read the paper, unexplained bump. And that bump was explained by measurements from not only Pioneer Venus orbiter, which again employed an eighth meter, not exactly the same design that you saw in the picture, but here, this is the spectrum of the far UV of spectrum of Venus obtained with Pioneer Venus orbit. This is from Sam Durance's thesis. Now, Sam Durance was a student of Charlie's here at Colorado, and after his PhD, he came to Hopkins in a trade for Tom Woods. He sent Tom Woods. Sam had a very good career at Hopkins because at that time we'd just been selected to build the Hopkins Ultraviolet Telescope for a flight on the space shuttle. And after he came to actually work on the sounding rocket program, and he actually flew a couple of rockets with me in the early 80s. There was a call for members of the science teams to participate in the shuttle mission as payload specialists, i.e. astronauts. So Sam, who in his previous career to being a graduate student in Colorado was a race car driver, decided that he would like to be an astronaut. So we lost him from the sounding rocket program, but he ended up flying on Astro 1 and Astro 2, and this is a spectrum of Venus that Sam was at the controls, pointing the telescope on board the shuttle at Venus. Again, I won't talk about what this is all about, but I mean, it's basically a huge bunch of CO4 positive bands. The red is the terrestrial spectrum from a patch of sky next to Venus that we needed to subtract. But basically, this shows you what can be done as the instrumentation advanced from Earth orbit. Okay, so we'll come back to Sam in a few minutes. So let's go back to the Mariners and the first application of the Ebert monochromator on Mariner 6 and 7. These are flybys of Mars, and here these are, as the caption says, not to scale, but every 3 seconds the spacecraft would move along its trajectory about 21 kilometers, and it would be mapping the vertical profile of the ultraviolet emissions above Mars. And here are the famous spectra of Mars. These are actually from Mariner 9, which was in orbit. In fact, the last time I visited LASP, when I saw Charlie, which was about 2 or 3 years ago, he was still working on Mariner 9 data. Now, we heard that he was working on nitric oxide a lot, but what he was doing with Mariner 9, he was taking the trajectories. Remember, it was in orbit about Mars. So he was taking the trajectories, and he had a student map them onto Google Mars. And then he was taking his ground tracks on Google Mars, and then correlating them with what was being measured by the spectrometer looking down at Mars at the time. It was a really remarkable thing to do. So somewhere in this building, or it was the other building at the time, is Google Mars with Charlie's annotations to it. Anyway, here's this spectrum where you see practically nothing down here, but it's clearly a very rich spectrum. So what I want to point out, just to make this somewhat relevant to what I'm doing, is that here are these profiles from the flyby. And you see they go out pretty far. They go out to 25,000 kilometers. Several Mars radii. And what you're measuring is escaping hydrogen. And you can't measure this very easily from a spacecraft in orbit around Mars. You just can't see that well. And so, this was a particularly fortuitous observation. And okay. So here is Sam's contribution, Sam Durance's contribution. We observed Mars the same way. I won't make the comparison between this and the Mariner 9 spectra, but here is something that we measured. This is now from the Rosetta spacecraft, an experiment called ALICE that Alan Stern of SWIRI down the street here is the PI, and I'm a member of the team. The comparison of what we did with ALICE, and again, you see the CO4 positive bands strongly attenuated. Here we're looking at the disk, so the very short wavelength bands are strongly attenuated by CO2 absorption. Okay, so what we did, the reason we got this spectrum with Rosetta. Rosetta is now successfully orbiting comet Churyumov-Gerasimenko and making all sorts of interesting measurements, and it landed a lander last November. But in order to get out to the comet, it swung by the Earth 3 times and swung by Mars once. That's when we got this. We also, thanks to some colleagues, who were searching with the wide field imager for a dust ring around Mars, which they didn't find. They made a number of offset observations. So here are the two observations, and you see we're actually going out the same as what Charlie measured, or the paper was actually published by Don Anderson and Charlie Ford. But here's again a fit, and what you get from we use Lyman beta. It's not as optically thick as Lyman alpha. Lyman alpha calibration is not too good. And then I won't go into the details of the analysis, but what you derive from a Chamberlain exospheric model is an escape rate, and our escape rate somewhere compares to what Anderson and Ford found. But basically, we reproduce the results. And of course, the major question remaining is if the hydrogen is escaping, then what happens? So this is you can now speculate over geological time periods how much water has evaporated from the surface of Mars. But then the question is, where does the oxygen go? And that's still up in the air. Presumably, we'll hear something about that from Maven. But anyway, I'm basically done. Let me just summarize what Charles Barth's legacy was for the ultraviolet spectroscopy of planets. He came up with the idea and sort of the rationale for putting UV spectrometers onto planetary missions. I think he just happened to be also in the right place at the right time. And the confluence of Charlie and Bill Fastie, they were an inseparable pair of friends, and Bill went, in the 70s and 80s. Bill got involved more in the astronomical missions and the Hubble Space Telescope, and Charlie kept going and working on the project you heard about Snelly, and you'll hear about SME later. And but of these single pixel monochromators, there are a whole bunch of them flying through the solar system. These are the sizes: the 6s and 7s were 1/4 meters, 9. Apollo 17 was a big 1/2 meter, and then these 8 meters. Even Jupiter, even Galileo had an 1/8 meter. And I apologize if I've left any missions off this chart. And UV spectrographs continue to be flown on planetary missions. They have great value in studying the upper atmospheres and plasma environments of both the inner planets and the giant planets. And a whole field of telescopic observations of planets began in the 70s with IUE, and then with Hubble Space Telescope and FUSE, and providing, in many cases, complementary information to the flyby missions, and in many cases, new and rare discoveries regarding planets and comets. Thank you.
So we have plenty of time for comments or questions or stories about UV spectroscopy of planets. Questions?
Yeah, there.
Oh, yes.
Paul, I was fortunate enough to overlap with Bill Fastie when I was here in the late 60s. And he came down to Wallops Island for my PhD rocket launch, which was a 1/4 meter Ebert-Fastie looking at the OH radical. And by that juncture, we were very good friends. And so I said, Bill, what the hell is the difference between Ebert and Ebert-Fastie spectrometer? Bill let out one of his great laughs and said, an Ebert-Fastie is an Ebert spectrometer with a thumbprint on the grating.
Yeah, there are several variations, Jim, on that story, which is there are a number of people who call it a Fastie Ebert instead of an Ebert-Fastie, and then there was a time he said, "Who's this guy Ebert anyway?" But it was a workhorse, and it was used on a lot of rockets. Yeah.
Just a comment on the connection between Fastie and Barth. At an AGU meeting several years ago, Fastie was up there to give a talk, and he somehow couldn't get started. He paused, and he had consternation on his face, and he hesitated. And finally he says, "Charlie, I need your glasses." So Barth gave him his reading glasses, and he could read his slides.
That must have been a long time ago, because Bill died in 2001.
It's a long time ago.
So, more recent UV spectrometers we have here have been imaging spectrographs. And there's still, of course, the same heritage, but I wanted to mention one point that people may not know, that for Mariner 9, it was a different era at NASA, and there was much more resources available, including several blocks of aluminum that could have been made into additional spectrometers for Mariner 9. And the aluminum oxidizes very slowly in the Earth's atmosphere, and these stood in the rain and storms on the back deck of the 55th Street facility where we used to build experiments here, until we inherited them on Cassini, UVIS, and we took those blocks of aluminum, part of the heritage of Mariner 9, and carved them up into the experiment cases. They're now in orbit around Saturn on the current UV spectrometer.
By the way, who knows what happened to Mariner 8?
Went to the ocean.
Went to the ocean?
Went up and went down.
Oh, okay. I knew it didn't get to Mars, but I didn't know where it ended up. Okay.
Ian,
Yeah, just part of its control system, there was a part that was dismounted 90 degrees, and that sent it into the Atlantic Ocean instead of to Mars.
Those were the days when NASA had enough money that they made two of everything.
those were the days. Yeah. I, of course, was in school at that time and very envious of one of my fellow undergraduates who'd gotten a summer job at JPL to work on the Mariner project. Of course, it was Mariner 8, and when it went into the ocean, he had to find a new job.
Hard to imagine how we would have handled two satellites in orbit at the same time back then.
Well,
That's
the plan for Mariner 8 was a similar orbit, or were they one was going to be polar and the other?
Well, there would be different orbits, so the Mariner 9 orbit ended up being a compromise.
Right. Well, I'd like to comment that Charlie was always working science, even back to the old stuff. And so one of the very last things that he and I worked on was this Google Mars, recalibrating the Mariner 9 data with the Solstice UV spectrum, and digging around and finding the Mariner 6 and 7 limb crossings. And we did that all the way up to the point where he didn't come in anymore. And so he was always that adamant scientist that he had to finish something that was undone.
Yeah, I know, because the time I mentioned when he showed me the Google Mars, I was at a meeting at SWIRI, and we just published our Mars result, and I think Ian came to the talk there, but Charlie couldn't come, and I wanted to come and show him the results, because it basically showed that the measurements made by Mariner 6 and 7 were really validated. And he looked at it, and he was very interested, and he nodded, and he said, "But I've got to show you this." That was Charlie, right?
Yes, Ian Stewart.
I hate to interrupt things, but don't tell all your stories about Charlie now, because there's an hour and a quarter after lunch with
Excellent, excellent. So, did you want to say anything about the ALICE results?
Yeah, we just we just have a paper accepted in ANA. We're observing the atomic species that you normally see in comets, but within a kilometer of the nucleus, and much brighter than you would expect if they were photodissociated. So they're due to photoelectrons. It's one of the things from Scott's chart. Photoelectrons produce, the sun ionizes, it's water, and then the gas coming off is immediately dissociated into an excited state. And it's interesting. I think we see very clearly hydrogen, carbon, and then the oxygen, which would come from water, CO2, and O2. And there's very little CO in our signatures. But anyway, the paper has just been accepted, and as soon as the powers at ESA let me, I'm going to post it on Astro PH. So sometime next week.
Super, thank you.
It's been very good.
Yeah, excellent. And that concludes this section. I'd like to break now for the coffee break, and be sure to come back for more invited talks starting at 11 a.m. See you then. Now this